video, we are going to be talking about lag plots and autocorrelation, and also talking about white noise processes that are very fundamental to um, understanding of time series econometrics. Okay, so let's first use some data and then get into lag plots. So the data set that we're going to be using today is coming from this data set called Australian Oz underscore production from the FPP3 dataset package, and you can use a pipe function on there and you can filter uh, and and extract all of the quarters that were post 1992 and beyond. Okay, and call that new production. So this is more recent production. You can call it recent production or new production. And notice over here we have a TS Sybil, and that has 74 rows and 7 columns, and it's quarterly data starting in 1992 quarter 1. Okay, and so we have lots of things over here, different things that were being produced, like beer, tobacco, bricks, cement, all of these things, but we're going to focus on beer. So let's take a look at a lag plot. What a lag plot does is it displays scatter plots of quarterly, in this case, quarterly Australian beer production, where the horizontal axis, right, your x-axis, shows lagged values of the time series against the time series itself. Okay, so this is like you're plotting yt against yt minus 1, yt again against yt minus 2, yt against yt minus 3, and so on and so forth, right? So you see all of these points. These different colors indicate different quarters. And so what is interesting here is that here's a 45-degree line, right? This is, we know that if points fall in this 45-degree line, you know, then it indicates a very positive, very strong positive correlation. Okay, so what we see here are two things. One, that the relationship is strongly positive at lags 4 and at lag 8. You see all of these points just falling on the 45-degree line. This is just basically saying that if you look at what's the relationship between yt and yt minus 8. Okay, so is there any relationship? The answer is yes, positive, right? So if we are thinking about displacement in a time series, if we are 8 periods apart, that is going to repeat itself, that type of seasonality. So this is very interesting to see for seasonality, and we can, from here we know going into our autocorrelation functions, when we look at the correlations between yt and yt minus 1, yt and yt minus 2, we know that at lag 4 and at lag 8 we are going to have positive correlation because of this chart. But we also see a negative relationship at lag 2 and at lag 6. Okay, and this is showing you sort of a negative slope here. If you think about it, it's negative slope here. This is because the beer production has troughs in quarter 2 and peaks in quarter 4. So if you think about, you know, the negative relationship occurs, why does it occur? The answer is because there is this is looking at what is going on to the time series now and 2 periods apart. This is or now and 6 periods apart. This is telling you there's a negative relationship. So you might have a peak somewhere, and then like 2 periods after that you might have a trough, and then so on and so forth. So this is showing a similar picture. This is just a scatter plot. In that previous figure you had all those lines that connect those dots. Okay, so now we want to move on and talk about autocorrelations. And autocorrelations are interesting, right? Because that would show you the linear relationship between yt and yt minus 1, yt and yt minus 2, yt and yt minus 3. So in other words, we're saying, well, how important is um, yesterday's value or the previous period's value to today? How important is of the value or the time series 2 periods ago, the value of the time series 2 periods ago to today, and so on and so forth. Okay, so this is what we're looking at. So again, sort of a recap here that, covariance and correlation both measure the extent of the linear relationship between two variables y and x. But so there are two important things. One is that we're looking at a linear relationship. In time series, we often come across nonlinear relationships, which we are not modeling at this point. But let's take a look at how does this apply to time series, because there is no y and x. There might just be a single time series that you're dealing with, right? So we talk about autocovariance and autocorrelation. Auto meaning, what's the covariance of y with itself, and autocorrelation is the same thing, correlation of y with itself, but we are looking at these relationships or linear relationships between the lagged values of the time series of interest. So again, yt and yt minus 1, yt and yt minus 2, and so on and so forth. So we've seen this in class that any sample autocovariance at any lag can be given by the following, where t is your sample size, right, the length of your time series, and this is basically looking at what's the covariance between yt and yt minus k. So this is sort of the expected value of this entire thing is the expected value of yt, the deviation of yt from its mean, which is y bar, and the deviation of yt minus k from its mean. Okay, and then if we want to get to autocovariance, this is just going to be this guy divided by the variance, right? So this is k is representing the lag, but here we are dividing it by C0. When the lag is 0, we're just saying this is just, denominator is just a variance of y. Okay, so what would R1 indicate if for correlation, right? So RK was correlation. R1 would indicate how successive values of y relate to each other. R2 would indicate how y values 2 periods apart relate to each other. But one thing to remember is that what matters in time series is just displacement. So the correlation between yt and yt plus 2 should be the same as the correlation between yt plus 6 and yt plus 8. Okay, and this is, when this is basically is going to help us in the future when we deal with stationarity, things like that. Okay, so RK, again, correlation is almost the same as the sample correlation between yt and yt minus k. Okay, so the one thing to remember here is that displacement matters. So now we can actually take a look at autocorrelation functions for beer. Here you can just use the ACF function. This is all in caps, remember that, and on the time series of interest, and we can say, well, give me the autocorrelation function for just 9 lags. Okay, so here it displays what the autocorrelation function is. We may even want to plot it, so all we have to do is, using the pipe function, we can say, well, autoplot the autocorrelation function. And so here you can see a chart where this guy right here is the relationship between yt and yt minus 1. So this is for displacement equal to 1. This is for displacement equal to 2. And this is for displacement equal to 4. This is for displacement equal to 8, right? Which is the lag structure measured on the x-axis. And then you are measuring correlation. So this is like a negative 1-to-1 interval. This type of a chart is called a correlogram, and here we are seeing sort of the same story that we were seeing in the lag plots, where 4 is at lag 4 and lag 8, you're seeing these peaks, positive, strong correlation, and at 2 and 6, you're seeing negative correlation, which is showing you what's going on with the data at that displacement. You can also take a look at a lag structure that's a lot longer. That way, if you want that, you can just get rid of that lag.max command or argument. And here we see that R4, right, the correlation at lag 4 is higher than that for other lags, right? So you kind of see these correlations diminish, which basically are telling us that as we go farther away, right, from YT into the past, at some point the relationship is going to break. And so these bars are significant at every 4 periods because of the seasonal pattern in the data. So beer production was quarterly, and so the peaks tend to be 4 quarters apart, and then all these negative correlations that you see here are because you have troughs that tend to be 2 quarters apart. So this is important just to conclude that when the data have a very strong trend, these autocorrelations for small lags tend to be large and positive. When data are seasonal, the autocorrelations will be larger at the seasonal lags. That is what we saw with the beer data. So this would be at the multiples of seasonal frequency. So if we have quarterly frequency, you would see that there's something happening at lag 4, then lag 8, and then lag 12, and so on and so forth. When the data are trended and seasonal both, then you would see a combination of these effects. So again, we're looking at US employment in retail trade, and you can kind of see here that there is a strong seasonal component to it, but also a strong trend component. So when we look at the ACF of these series, you kind of see this scalloped structure, you know, kind of going up and down, and this is due to the seasonality that exists in every 12 periods because the data are monthly, and so this is showing that your autocorrelations are larger at the seasonal lags of 12, which matches with the frequency of the data. We can also look at Google stock, and this is a little bit, you know, it takes a little bit of effort to get to the autocorrelation functions when you're dealing with stock data. You have, this is a preloaded data set, GAFA stock. You can filter by symbol, which is Goog for Google. You can also say year date equals 2015, you know, so that would just give you all the closing prices of the Google stock for the year 2015. And this is what it looks like, right? So you can see that you have daily data, but you see that there is like an exclamation mark over here, which is not showing us the frequency of the data like it used to. So this is indicating that there is a TSable that is at an irregular interval. So we need to fix this. But first we can take a look at the plot of the Google stock, right? So see, it has been climbing up since 2015. We're just looking at a 1-year interval, but this is like a sharp increase over here. And again, like it says date exclamation because it doesn't really understand what is the frequency. So if we try to do, we try to look at that data set and we say, well, ACF of the closing prices of Google and the lag structure is 100 periods, it's going to throw an error, and it'll say that it cannot handle a TSable of irregular intervals. So we need to fix this. And how do we do that? There is a little bit of a snippet that you have to type in. You have to say, well, Google to 2015 pipe function, you want to mutate, and you want to say trading underscore day. You want to construct this variable equals the row number, right? So what you're doing essentially is that you're creating an interval for the trading days, like in a particular year.
I found these results.
So this happened in class 2 where my Google phone recognized my voice and it doesn't like the fact that I'm talking about Google. Anyway, so what we can do now, and we can use the pipe function again, we can say update underscore tsable, right? So I'm going to update this tsable that I had before, and I'm going to say the index now is the trading day, and it is at regular intervals. So put that equal to true, and notice over here, this is now, it's all good because it's showing me trading days at one period apart, right? So this is 1 day apart. And now it's all good, and you can actually take a look at the autocorrelation function of the Google's stock closing prices for 100 lags. And here we can see that the data have a strong trend. These are the positive, strong, large autocorrelations that we see, and that's what's going on. So you can try a few things on your own. This would be a good time to stop the video and work on these examples where you can look at different types of functions that we introduced, the GG underscore lag function and the ACF function, and you can use these functions to explore different time series and then comment on what you're finding. So this is a question that I'm going to throw on your homework. This is a very interesting question on can you match the time series with the autocorrelation function, and so you'll have to do it by next week. Anyway, this is the last thing that we're going to talk about is white noise processes. These are time series that are sort of the building blocks of time series econometrics, but these are time series essentially that show no autocorrelations over time, right? So anything that we were seeing that was positive, any positive or negative correlation is not going to be seen. The autocorrelations will essentially be zero. So first we're going to generate a white noise process. A white noise process is just, like I said, is uncorrelated over time, right? When we say uncorrelated, we are talking about a linear relationship between the data, like y with it lags of itself. It's uncorrelated over time, so it does look like sort of this series that goes haywire over time. What you can do is like generate a white noise process by setting seed equal to 1 here. This is just like a number generator in R. It's not necessary, but if you want to replicate the exact same thing that I have here, you would be able to do that. So let's set .seed 1 and then create a white noise process, which is just a TSable with the time being a sequence of 36 points, right? So we have 36 points here, and then we are generating y as a random normal. And again, with 36 values, and we're gonna, again, this is a TSable, so we're gonna call the index, which is just t that we define right here. And we're gonna auto plot y. So this is what it looks like. And what is interesting is not the plot itself, but to look at the autocorrelation function of this. So when we look at the autocorrelation function, notice that you have all these correlations that are falling inside the Bartlett bands. These are the Bartlett bands that tell you whether these correlations are significantly different from 0 or not. And here you have correlations that are measured, right? So if you don't want to look at the bars, you can look at the numbers here. They're all so close to 0, and none of them is significant. So why is this important? When we do forecasting, and we are looking at exploiting data that we have, or the information set that we have in our time series, and we use it for forecasting, ultimately we want to look at our errors, and our errors should always look like white noise processes. Because we should have exploited, if we are building a great forecasting model, we should have been able to exploit any type of pattern that exists in the data. So any type of residual or error term that's left from our forecasting model should not display any pattern. It should look like it's haywire. It should look like it has an autocorrelation function of something like this with zero autocorrelations. And that would tell us that yes, we have exploited the data and we have extracted all of the patterns that existed. Okay, so here what you're seeing is sample autocorrelations for white noise processes. This is going to be close to zero. The blue lines over here called the Bartlett bands are just the 95% critical values. Okay, typically for the distribution, this is just more theoretical. You can skip this if you don't like. But for a white noise data, the sampling distribution asymptotically tends to a normal distribution with mean 0 and variance 1 over t. And so the bands that you see, those lines that you see, they are just plus minus 1.96 because they're 95%. Confidence bands, this is just plus minus 1.96 divided by the standard deviation of the time series itself. So we want all of the autocorrelations to lie within those bands. We don't want any autocorrelation to cross those bands, because as soon as it crosses, it's showing you that there is some kind of a pattern that exists in the data. Okay, so you can take a look at different types of examples in the slides, but one thing I would like you to do is that you can compute the daily changes in the Google stock price, right? So we had looked at the GAFA stock preloaded data set, and we had extracted Google out of that, and we had made some adjustments so that there's no trading day irregularities. But what I want you to do is this one last step, which tells you mutate this data set and now look at the difference in the closing prices from one day to the next. So you're looking at the change between today and tomorrow, and you're doing that for the entire data set. I want you to look at the autocorrelation function of this and also just plot the series, the differenced series, and see what you find.